So, good afternoon, students. Today we have seen how to use MSc Adams for our machinery tools. Here I am Zahir Khatib. Now we have seen how to use the Adams machinery. Is this module contained in the Adams view module? First, look into the screen, asking for the new module opening, existing module calling, and exiting of the app. Click new model. Overview, ask for the detailing of the model. The model name we can see is the simple belt analysis. For first time we can say it is first. After that it asks for the gravitational. Normally we know this is the x-axis and this one is the y-axis. Normally the earth normal is on the y-axis, so you can say as a y-axis. After that we need to set units. So all the dimensions are in millimeters, kilogram, newton, seconds and degree. Here it can ask for the directory. Here I am showing the directory path as at the Adams machinery. Now we can say it's apply and OK. After that the message window shown, the whatever we have set as a primary, few shown in the error command, but it looks and save on the same location. Now we can close whatever the screen. Now you need to add those things. Here few are the distractions. Okay, now I'm trying to avoiding those things. Okay, now you people are able to see clearly whatever over the screen. Okay, so just I'm adjusting the screen. Now you see the Adams view offering a lot of things regarding the solid modeling, the flexible bodies, the curve structure, the Boolean operations of add-on, subtraction, union. Okay. After that, they also added the features. Okay, so we can chamfer it, we can uh, cross section. Okay, so all the things are available in the Adams view. Now our main motto is how to perform the machinery operation. Now once again I am introducing myself. I am Zahir Khatib. I have a rich experience of 9 plus in the field of analysis. Now you can see the selection of machinery command. In that the Adams machinery is the most preferably used in the all SPM manufacturers. Those are using the gears, those are using the belts, those are using the chains, those are using the bearings, cables, motors and camera related activities. Here this is a very simple modular. I am trying to explain those things in a very simple language. First of all, we need to create the pulleys. So just click over the pulleys. In that pulleys, we need to define the proper function of the belt system. So we can see is the belt system 1. The name is belt pulley. Okay. As now we can say is a smooth. So they are offering the 3 types, which is the V groove. We know the V groove, which is the axis to axis matching on those things. So groove to groove match. After that the trapezoidal, you can see the belt is like trapezoidal, or on the pulley is also the trapezoidal. Okay. Now the toughest and commonly we people are using this smooth pulleys. So we can select here a smooth. Now the secondary, we need to define the method of analysis. The first one is the constraint. In that constraint, we only calculated the speed reduction and the multifunction of its interest. So we people are avoiding the constraint level. After that, the 2D link here we people are using for the faster simulation and calculating the contact forces between the segmented and pulleys. Now the 3D link you can see here. So most of the times we people are using the trapezoidal. So at that time we need this type of the 3D links. Also the most important thing, when the axis of rotation is not a parallel, okay, to the global axis, so that's why we need to use a 3D link. Okay, please, the axis of rotation is not a parallel. Okay, now you can see the 3D link which is a non-parallel. You can see the misalignments in the pulleys. We need to use these 3D links in the non-planar mode. Okay, so this is 3D simplified. Here the pulley size and belt size is totally different. The roller distances and the few spans. Normally this type of linkage is normally this type of pulleys were not used in the industries. So we prefer most important things which is the 2D link. So 2D link offers the faster simulations. 2D link offers the calculating the contact forces between the segmented and pulleys. So here we go through the next level. So we can say it is a boundary conditions of this whatever we need to define in that. Okay, so here you can see the first and second, there is a two pulley. Okay, we know basically in the belt. So here the name, first one is the driver. So we know the driver for the belt system. Now he's defining the central location. Now I can see I'm just push back my pulleys to the center distances. I can say in the coordinate 150, 0, 0. Now we need to define the pulley width is a 30, okay, and the pitch pulley diameter we can say it is 50, okay. So what is pulley pitch diameter? The pulley pitch diameter you see in the formula, okay. So this pitch will form for we performing the continuous transmission of the belts, okay. So that's why this is the pitch pulley diameter. Here I'm defining a 50, okay. So in the second pulley, okay, the number of pulley is 2, so that's why second pulley. The name of this pulley we can say it is a driver. Now the central location I am defining 150, and here we can say it's a 200, 0, 0. So we can say the difference between these two pulley is the 200 plus 150, that is the 350. Okay, so pulley width is the same. Now we can say the pitch of pulley diameter I am increasing with the 50. So just the bigger pulley, the distance is higher, so that's why we need to add those things. Okay, so the pitch diameter we can see the difference. Okay, in the first we can see the 50, and second one we can see the 125, means the second pulley is bigger than the first one. Okay, so driven pulley is bigger here. Okay, now go to the next command. Here we need to define the materials for the pulley. So normally you can say the setted is a steel material. If you people are not happy with the steel material, you need to go through that and change the materials. Okay guys, so here you can see the lot of materials option is here. The wood, titanium, lead, copper, brass, glass, nickel, magnesium, okay. But steel guys, okay, so normally we people are offering the steel materials. So we know the density, the Young's modulus and the Poisson's ratio. Okay, for our information they shown. We people are unable to edit these values. Okay, if you people are using any grade of the steel material, then you need to choose as a add a material. Okay, and you just change the values of the densities, Young's modulus and Poisson's ratio. Here we say it is the next module. All these things, okay, all these pulleys, okay, we can see the pulley 1 and pulley 2, all those are rotational movements, but the body of those things are stationary, so we can say it is ground. Okay, so here I'm just putting the ground value here. Okay, for the secondary one also we just putting the ground, so we can say we just fix the pulley of 1 and pulley of 2. Okay, so 1 and 2 pulley will be fixed at whatever you can say is the mounting hub. Okay, now we can go through the next command. Next we have need to set the motions. Here they are offering angular displacements, angular velocities, angular accelerations and joint force. Now we can say to the next. So here the tensioning device we need to be defined first. So next, so tensioning we can see the only zero tensioning I am defining here because we don't know where it is the tension. So now we can go through the next command, and after that make it the finish. Okay, so you people are seeing over the screen. Okay, this is the 2D diagram. Here you can see in the right bottom side, here is the wireframe to the shaded, here is the changes. Now also you have an opportunity here to see the zoom path here. Now you can see in the zoom view, here we can see the rotational motion. So you can see here the width is 30. Now you can see the difference between those things. This is the 50, this is 125. Now you can say the difference between this is 150. Now this is difference between this is 200. So it is a 300 is the center to center distance. This is a linear. This is a 30. Okay, so all the boundary condition will be defined first. Now we need to move towards the rotationary. Okay, so just pulley I am setting here. Now I need to create the belt first. So just belt. Now you can see the pulley set. So we know these things. We have the guessing language here, the bullet one, which is the pulley set one here I am defining. Now I can see the 2D links, whatever I am method I am first of all defining those things. Here the segmented length. Okay, so segment length of the belt. Okay, so this is the geometry of the belt we can say. So segment we can see the 7.5, 10 is the standard. Okay, so just I am defining one standard segment length. Here is the 10th, and a belt height we can say here the 3. Okay, so just I am reducing the size because we need to find the deflection over there. So we can say here the next. Okay, in the next we can say the belt segment, there is a mass, the center of mass. Okay, so inertia they will be calculated first here, and now you can see the contact parameter and the friction parameter. Accordingly they will defining. If we want to change the values, then we can change it, but my opinion, okay, so this is the by default values. Okay, so don't change those things. Okay, if you have a perfection in that the penetration depth and whatever the scale factor, so you need to go for that. Then you can see we need to define the wrapping order. So how we can wrap this belt over these pulleys? Okay, so we need to define first. So we know guys, first we need to drive, we need to wrap the belt over driver. Then we need to move toward the driver. Okay, then we can see the next module here. Okay, here the wrapping of the belt, you can see the tension is calculated in the newtons. Okay, so 98 segmented we found because due to the distances, the 150 distances, they are creating the 98 segments. The whatever the tension over the belt is minus 549 newtons, so we need to calculating those things. Okay, after that the strain in the belt, so we know that the standard belt strain is minus 0.18%, so accordingly they will take in those things. Now you can see the span request and it is a segmented request. So first we need to define the span. So belt span, we need to define the part guesses. We can say the belt segment 1. So the reference part, we can say it is the ground. Okay, every time we need to define those things. Okay, so belt part for the segment 1 and the segment 2. Okay, I'm not forcing whatever the averages, whatever the motions. Okay, here in the link part we can say, okay, here we need to add the guesses, which is the belt segment 1. Here there is no segmentation, so we can say it is click and finish it. Okay, here you can see guys, the belt is here. Okay, so just I'm trying to move those things. Okay, so you can find how it is exactly looking. Okay, so just I'm defining those things. Okay guys, so here if something is mishappening with that, okay, so we have a lot of options here. Okay, so guys, you need to know. Okay, so this is the driver, this is the driven, the gravity is shown here. Okay, so there is a number of things are happening here. Okay, so you can see guys, there is a lot of things. Okay, uh, then we need to find how it looks. Okay, so just I'm adjusting the views. Okay, so guys, okay, so you can see here clearly. Okay, the belt one, the gravitational force is on downward side, the river flow. Okay, so after that we need to motion it. So first we need to find out the name by the pulley set 1. Now we can see the driver pulley here. Next, here we can, they are asking for the type. Yes, we need to find the torque. We know the motion, here is the constant motion. Okay, so set it. So we know the motion is constant, so we didn't go for the harmonic or the curve like user defined thing. So constant, we can see here the value is 150 rpm. We can say the 150 rpm clockwise direction. The geometry scaling is 1. The activity is on. Now we need to find the motion here, the angular displacement, angular velocity, angular acceleration. Both three are our requirements. Also the torque we need to be applied over that. So we can say it is completion message. So it is finished. So here you can see over the screen guys, there is a simulation here. So we need to click the simulation. We need to simulate the values. So run the interactive simulation here. So here the end time simulation we can adjust, it is 15 seconds. So we need to see those things, and steps is 150. So we know the distance is 350. So just I am adding those things here, and here we can see the run here. So you can see over the picture guys. Okay, in the screen you can see the how the belt is running here, how the traces, okay, how the forces are acting over that. So here is the one segment. So just I'm defining here. Okay, once again I'm calculating those things. Okay, you can see here. Okay, so you see the y direction, you see the x direction. Okay, you see the segmented factor here. Okay, so we need to calculate the point. So plotting is done. So yes, we need to add animation here. So first animation, then it is plotting. So plotting the page. Now you can see the two pages here. Okay, so just adding here divided by 2. We need to show here the animation. So load animation. After that we need to add the simulation here. So just they are adding the simulation. So we know the last one is here, the simulation factor. So we need to calculate and filtering the displacement, velocity, acceleration, force, and the user defined things. But here, as I requested the result set, we need a result set on the driver side. So the belt 1 I am considering, and here the belt 1 segmented. So actual contact force is required to calculate. So I am adding the curve here. Okay, now I'm run those pulley. Okay, so you just see guys. Okay, so whatever the highest things is here. Okay, so the run, so just I'm stop it. Okay, where it is actual force. Okay, so you can see guys here you can see the actual forces. Okay, so maximum stress point is here, so we need to adjusting those things by changing the dimensions. Okay, so also we have a lot of things are happening. We need to set the limitations, we need to set whatever the valuations. Okay, now the file exporting and the spreadsheet. Okay, so spreadsheet name is there, so result. Okay, and you can see the result here, name, apply. Okay, okay, so here you need to add both the things, the normal contact forces, belt tensions. Okay, so you need to add those things, but we need to calculate only the actual contact forces. Okay, so yes, I'm closing here. Now if you need to check those things, the last simulation, so we go through that and find out how the simulation will be done. Okay, here you can see the segmented. Okay, so also you can see here in the downside the completion of those things. Okay, so this is a complete simulation done by the simple belt analysis. Now you can see the result. Here is the post processor in the Open Adams processor. So in the Open Adams, you can see here the post processing values, and I'm already explaining. Okay. So here the spec line we need to define. If I say my 0.15 force Newton is the highest value, so I need to define the 0.15 on the y-axis for apply and OK. So here you can see the set limit in the blue line. Okay, so accordingly you need to calculate, you need to judge. Okay, so you're just finding those things. Okay, here. So guys, hope you understand how to perform the simulation of the simple belt analysis. Here I'm just save the database. Okay, after that I'm closing the file here. Okay, so guys, hope you understand how to perform the belt analysis. Okay, you people are happy with the sharing. Okay, please like and share my channel back.